I think it's 5 past. I think we should get started.
Okay.
So like this time we have like Justin from Intel presenting, and he's going to talk about some exciting work he's doing in the direction of like learning enhanced programming. With that, Justin, it's all yours.
Perfect. Thanks, Tim. And let's see if that worked. Can everyone see my screen?
Looks good.
Okay, wonderful. I'm going to just try to minimize this thing over and start my timer. Okay, perfect. So first of all, thank you all for joining, and thanks especially to the DCL folks for giving the opportunity to give this talk. As some of you know, I oversee the machine programming research at Intel Labs, and I'll be talking a little bit about some of the projects that we're working on over here today. Before I get into that, just keep in mind that your performance numbers may vary, and that's to be expected. So let's dive right into machine programming research. The first thing I think that's important to acknowledge is that machine programming is a pioneering research initiative at Intel. And what that means is Intel is sort of committed to it for the long haul. There are only a handful of projects and initiatives that are in the pioneering category. The fact that machine programming is, I think, is very promising and really encouraging to folks like myself and Tim Matson, who have been trying to establish this MP direction for quite some time. And now that we are pioneering research, it essentially means that Intel will be committed to this, hopefully for several decades. Very quickly, to dive into some of the higher goals of machine programming research, they really break down into these two categories. The first is we're trying to improve the development time for software. So all aspects of software, one of our sort of end goals is 1000x improvement over the work that humans are doing today. And keep in mind, for pioneering research efforts, the goals are meant to be a bit audacious. So we realize 1000x is quite a bit. On top of that, we also have a quality concern that just producing software 1000x faster, if the quality of the software degrades, I'm not entirely sure that that's a win. So we also want to ensure, as we're developing that software more quickly, that we also are ensuring certain quality characteristics like correctness, performance, security, maintainability, portability, these types of things. And the metric that we tend to think about when we think about this is against human programmers. We're really shooting for things like superhuman quality characteristics, superhuman performance. And although these may seem a bit crazy, there's actually early evidence in things like Halide's autoscheduler, where they are already seeing over 1000x improvement in the development of those autoschedulers compared to Ninjas. And then they're also getting performance that is exceeding the performance of those expert software developers. That is constrained. And so one of the core goals here is to see if we can generalize that type of thing. But before I go any deeper, I'd like to quickly recognize some people that are involved in machine programming, and my advanced apologies if I've missed you. So here what you see are a number of people that we're collaborating with in machine programming. In this top row, we have a lot of the core team and many of the people that are involved in the day-to-day of machine programming research at Intel. I also want to point out that we are collaborating with several professors at MIT. So Tim Kraska, our expert skier that we know from last time, and that's Jonathan Reagan Kelly and Armando Solar Lezama, actually at Intel Labs Day in December, speaking with me on machine programming. I also want to just quickly acknowledge some of Intel's DCL champions. That's Nesime Totbull and Tim Matson in his sort of native habitat. I won't talk about how bad Tim is as a kayaker, because I think he's the opposite of that. And we'll probably end up seeing videos of him next time. So that's Tim, that's the other Tim. And then also Greg Leeming, who is the program director from Intel side. Lastly, I want to point out that Gabby Cruz-Thompson is the director of University Research Collaboration. Gabby is largely the person that all of us are in some ways beholden to, as she essentially controls a lot of the funds that Intel will give to these university collaborations. Before I go on to machine programming, I want to call out just a few people that have won this exceptional thing. The first is Wei Wang. Wei and I and some others at UCLA are working together. Wei just received this 2020 ACM Fellow, which is, as many of you know, this prestigious award, prestigious title. And Wei, Yizhou, and Roshi and I are working on this thing called the Program-Derived Semantics Graph. We'll talk a little bit about this later in the talk. But since we're talking about ACM Fellows, it kind of feels necessary to also call out a couple others that made the 2020 list. Remzi, who, as some of you I suspect know, are working really closely with Microsoft Research and the Gray Systems Lab at University of Wisconsin. And then our very own Sam Madden, who's the co-director of DSAIL. And my advanced apologies if I missed anyone. And then lastly, I would like to call out this crazy guy. This again is Tim Madsen. And I want to just quickly share that Tim is in some ways the visionary behind DSAIL. That DSAIL was originally started at Intel from a pitch that Tim made. And then he started coordinating with MIT. And then we pulled in Google and Microsoft. And then this amazing thing happened. More photos of Tim. Tim and I have worked together for the last 5 years, and he's deeply involved in DSAIL. He's also deeply involved in machine programming, which brings me to an interesting thing that Tim said to me just a couple days ago or a couple weeks ago. He said that I can't give a talk without mentioning the 3 pillars of machine programming. And what I found over the last 5 years of working with Tim is he's pretty much always right. So let's talk about the 3 pillars. This is a joint paper that we wrote with MIT back we started writing it in 2017 and published it in 2018. And it really tries to create a nomenclature and the vision for machine programming. So at the highest level, machine programming is really about the automation of software and hardware. And the way that we think about it at Intel Labs and more broadly across Intel, and I think some of academia as well, is in these 3 spaces. The first is intention. What intention attempts to do is help us build systems that can understand humans better so they can express themselves in various forms. The current way that we do this is through writing code, but the goal is to move away from the 27 million programmers of a global population of 7.8 billion people, which is less than 0.5% of the global population, to instead enable all people to be able to communicate with machines and then create their own specialized software. So we may have things in natural languages, visual diagrams, gestures, what have you. There's plenty of room still for code, but the idea with these intention systems is to explore new ways to have people express themselves to machines. It's also concerned with the idea of lifting meaning from existing software. Because we have billions and perhaps trillions of lines of code out there, there's plenty that I think that we can learn from that software. Unfortunately, the lifting the meaning from these existing systems tends to be non-trivial. And this is something that we at Intel Labs and in the machine programming research group thinks is fundamentally important. Once the intention of the system is understood, then we hand that off to an inventive system. And what the inventive system aims to do is create a higher order representation of the algorithms or the data structures for fulfilling that intention. And in many cases, it's not actually inventing something completely novel. It's really taking existing components and composing them in ways that fulfill that user's intention. However, I will say that there has been some work recently that seems to indicate that some of the machine learning systems are actually inventing something that is truly novel. Once we get through the higher order invented system, we then move to the adaptation pillar. And what the adaptation pillar is about is principally taking that higher order program, lambda calculus in the form of a DSL, something of that nature, and then lowering it to work efficiently, correctly, securely in a specialized ecosystem. So the hardware and software that it's being placed in. And a really simple way to think about this is if you have a sorting program that's going to potentially run on a handheld device that's sorting maybe a couple kilobytes of data, the algorithm is probably going to be vastly different than the same sorting algorithm that then is going to run on a data center that's going to sort perhaps petabytes of data. So this is why the adaptation pillar is so critical and why it's separate from invention. And then lastly, you'll notice that data is part of all of this. What we're probably going to talk mostly about in this talk is how the research we've been doing at NPR is creating new challenges in data that hopefully will resonate with some of the DCL folks. I also very quickly want to point something out that I think we joked about in 2019 about Software 2.0. I want to just make it very clear that in Andrej Karpathy's original blog post in 2017 on Software 2.0, he explicitly said that the way he was thinking about it is neural networks will essentially replace software. And while I think that there's certainly a place where neural networks can be used to replace software, I think that that definition is a bit narrow for a variety of reasons. First of all, I think that code has certain capabilities that neural networks currently don't have, such as interpretability, debuggability, these types of things. Also, there's more to the world than just neural networks. I think that, as you'll see in this talk, there's some interesting stuff going on with genetic algorithms, and there's very interesting stuff going on with Bayesian networks. So machine programming is much bigger than Software 2.0 if we think about it as just using neural networks to replace code. In fact, when Tim Mattson and I tend to think about machine programming, we usually define it in this space, that there is a stochastic side. This is the space where we tend to find the machine learning systems, but it's really any type of system that is probabilistic in nature, that uses some sort of statistical reasoning to get you your result. On the other side, there is a deterministic solution, and this is more where the formal methods fall, things like SMT and SAT solvers, these types of things where you have formal mathematical guarantees for the systems that you're building. And coincidentally, we actually just had Giovanna from MIT, one of Armando Solar-Lozama's students, give a talk at Intel Labs yesterday. And so I was able to change these slides to incorporate how Armando, who is overseeing the NSF expeditions, understanding the world through code, who I'm super gracious to be part of their advisory board, how they're thinking about this as well to sort of make it more concrete. So if you look at the way that Giovanna and Armando are thinking about this, this is sort of taken directly from Giovanna's slides, is that on the left, you have the stochastic side. This is sort of the neuro side of neurosymbolism, where you have a bunch of data, you then churn it through some machine learning thing and out comes a model. On the other side, you have a deterministic, something seems, oh, there we go. You have a deterministic system where it is taking a specification, potentially in the form of input-output examples, and also using certain language constructs and potential representations, sending that through a formal synthesizer, and out comes a program. So hopefully this sort of concretizes the concepts of the stochastic and the deterministic in the form of neurosymbolic research. But one question that we have is, where does this data come from? And what I can tell you is, from my own experience, a lot of us are kind of making up as we go. That you'll see concrete examples in some of the systems that we've built where we have lots of data and we have ideas about data, but because we aren't data scientists, we aren't experts like many of you are at DSAIL, we don't necessarily know that we're making the right choices. So it would be, I think, wonderful to get feedback on ways that we could potentially improve gathering this data. So for the remainder of this talk, I'm going to mostly focus on debugging, and I'm going to try to emphasize the open challenges that we've been seeing. I want to quickly point out, though, that there are dozens of machine programming projects at Intel. We literally have hundreds of researchers and engineers working on it now. It's really sort of taking the company by storm, which is super exciting. But the topics we'll take a quick tour of today are the following. We'll talk a little bit about performance regression, a little bit about code semantics, anomalous code detection, and then a little bit about program synthesis. And because I only have 15 minutes left, I'll make this faster than I would normally. But hopefully, if you have questions, we can take those potentially offline. This is probably something that everyone on this call knows, but just to quickly walk us through debugging, what we really care about with debugging is we don't want the quality of the software to degrade, especially as it changes, that we have some sort of bar that we expect it to meet through testing or certain correctness or performance. And what we find is that as the software and hardware changes, even the software and hardware that's outside of our control, what happens is the quality of our software tends to degrade. And these reductions in quality tend to be known as bugs. The process of debugging is really taking some sort of investigation where we can observe root cause and eliminate those bugs. But one of the first questions that you may have is, well, why would we focus on debugging rather than something else? If you look at a study that was done in the University of Cambridge in 2017, they basically did an analysis of the entire global cost of software development and saw that of the 1.25 trillion US, 50% of that was debugging. So that roughly equates to $625 billion. And that was in 2017. I think that I saw the numbers more recently, and it's closer to 3 trillion. So essentially, we know that 50% of software development costs is debugging. On top of that, there's no one that I actually know that likes to debug. And when I tend to talk about machine programming, some people get nervous about automation. When I talk about automating away debugging, I really haven't experienced any pushback from developers saying, oh no, please, I want to continue to debug. So I think that this is a good area for us to make strong headways for machine programming. So let's start with the first topic. We'll look at performance regression testing. If you're not familiar with this, it's a pretty simple idea that you have an existing program, you're then modifying that program, and then somehow the performance has degraded. So why should we care about this? Well, it turns out that many of the large-scale pieces of software that we have, one of the most important types of bugs they care about are performance regressions. And part of that is they are very challenging to detect. If we look at this example in MySQL 5.5, what we see sort of in abbreviated fashion is that two threads are contending on the same piece of memory through a globally shared lock. This is a pretty naive way to implement this system. So instead, the MySQL team went and improved this by creating a vector of locks and a vector of pieces of memory. And so each thread has its own lock and it upgrades its own piece of memory. And then when you need to get the summation of all the data, you grab all the locks and you add things together. What they didn't consider, though, is that this invokes false sharing on cache lines. And the result of this was actually a 67% reduction in performance. And that code went into production. So with that in mind, we built AutoPerf. We published AutoPerf at NeurIPS 2019. Here's some of the team. This is Mejba, Abdullah, Nesime, Tim, and Javier. And what AutoPerf does is essentially, going back to 3 pillars, is that it invents and adapts the tests that it's generating to specific hardware. If you want to take a quick look at the system model, it uses 3 primary components. It uses zero positive learning, which is a form of learning that only looks at the negative space, in terms of anomaly detection. This is the normal space. It then learns from that normal space on what the expected behavior is. It then uses autoencoders, which is a particular form of neural networks, to then try to understand that normality. And then if data falls outside of the reconstruction error for the autoencoder, it flags it as a performance anomaly. And then the last component is it uses hardware telemetry. And this is sort of the key component that we saw, that when traditionally you try to attack some of these problems in software, you can oftentimes introduce the Heisenberg effect, which has the byproduct of actually hiding the bug that you're looking for. But what we found with the hardware telemetry analysis is that the performance overhead seems to be low enough to where, at least in our experiments, we were able to capture all of the performance bugs. But one of the major problems that we have in this space is we need more real bug data. For this paper, I think we looked at about 10 different real world bugs and across 7 different applications. And that's a really small number. So one of the data challenges that we currently have is if we want to make forward progress in the space, we probably need some sort of benchmarking data set of these types of bugs that we can learn from. The next topic that I'd like to talk about are code semantics. In case you're not familiar, code semantics are essentially the meaning behind the syntax. And if you were present for Brian Cross' talk a couple weeks ago from Microsoft, he talked about how one of the things they're trying to do with learning optimization opportunities is being able to express in some sort of form to the machine the semantics that they're trying to identify in the code. So there are many reasons why we might care about code semantics. Brian's example, I think, is actually a really good one. And if you haven't seen that talk, I strongly recommend you check out the recorded version. So in order to start to tackle this problem, we have built something called the program-derived semantics graph. We presented this in December of last year at NeurIPS at the computer-assisted programming workshop. My colleagues are shown here. And you may be asking, for this PSG, which is a hierarchical representation, why do we want it to be hierarchical? So if we're trying to understand semantics, isn't it enough for us to just have like potentially a flat layer? Well, to look at this more concretely, one way to think about this is that if we look at an implementation of exponentiation implemented recursively, you see this code here on the right, and on the left, you see the corresponding PSG that would be generated. When you then implement exponentiation iteratively, it builds the corresponding graph on the left. And what we find with PSG is that compared to Aroma's simplified parse tree, it seems as though there's a greater degree of graph node matching, which could give us an indication that the semantics of these two implementations are similar. On top of that, one of the things that the hierarchical representation gives us is it allows us to look at various different levels of things. So for example, one might care about the fact that one of these implementations is recursive and the other is iterative, because we may be working in an embedded compute device that has a limited amount of space and the call stack could be blown if you use the recursive solution. Alternatively, you may want something that has fewer branches because of execution speculation, branch prediction. So there's various different reasons why we might want different levels. And so this is one of the benefits of the PSG approach. We also are working on another system called MISM, and a number of people are involved in this. In fact, Tim Kraska from MIT is involved, as well as Ryan Marcus. And the MISM system offers us two advantages that we see for semantic reasoning. The first is we also create a new representation called the context-aware semantic structure and a learned scoring algorithm. And you can see an example of these two things here. Due to time constraints, I won't be able to talk about the CAS much, but I'll tell you a little bit about how the learned neural scoring algorithm works. So the way that this starts is we take a code snippet. Right now we're looking mostly at C and C++. We then do a featurization into the CAS structure, and then that's passed to a machine learning, a twin Siamese network on a DNN that actually learns the semantic scoring algorithm. And the reason why we think this is important is that different structural representations of code may require different scoring algorithms. And then once that's trained, then we feed the learned system down to the inference. It continues to have the same first partition of the code into CAS, and then uses the learned portion to give us a similarity metric. And the similarity metric here is about semantic similarity. What we've seen is when we compare this to 4 different state-of-the-art systems, overall MISM seems to perform really well. We don't have time to go into the details, but if you're curious, you can find the paper on arXiv. We have tested across 19 million lines of code, 350,000 full programs with 400 unique classes. So a pretty decent range of data has been thrown at it. But one of the questions that we have here is, why would we stop at 19 million lines of code? And a lot of that has to do with the fact that there's just not enough labeled code data. So this is another challenge for the DCEL folks to potentially be thinking about. The next topic is in finding code anomalies. So we also were at NeurIPS presenting this paper. This is Neurogen. And what the control flag system does is it tries to identify anomalies in these control structures. Control structures are things that control the flow of a program. So things like if statements, for loops, exceptions, whatnot. And because control flag is self-supervised, we were able to learn from over 1 billion lines of code. But rather than telling you about it in words, I'm going to show you a quick video. And I want to apologize, you might see a little stuttering at the beginning of this video, but then it should smooth out. So this was shown at Intel Labs Day just a few weeks ago.
Control flag trains a model to learn typical programming patterns using a dataset of known good example code. It can improve over time with larger datasets and adapt to changing coding techniques. Once trained, control flag scans target code for idiosyncratic programming patterns. This method can find logical bugs and inefficiencies that aren't caught by modern rules-based compilers. Just as an example, here's a classic coding error. Here I'm trying to compare if x is equal to y. But you can see I've made a mistake. I've used only 1 equal sign instead of 2. So rather than comparing if x is equal to y, I've actually set x as equal to y. Now this is logically correct and it will compile, but it will produce unusual results. This is the kind of problem that control flag excels at catching. Now this example is such a common mistake that many compilers will have a rule to catch it. So here we wanted to test control flag on some real world code looking for unusual usages. Curl is a library used to transfer data. It's used in cars, set-top boxes, routers, and thousands of software applications. We ran control flag on curl looking for unusual usages, and this UI here is going to parse through the results. Here we're running, looking at 23 files with an anomaly threshold set at 1%, looking for things that occur in less than 1% of similar usages. And here it found something. This says keep on is greater than true. So what's keep on? Here in the source, we can find that keep on is actually an integer. Keep on is set here is equal to 2. So keep on is an integer and true is a Boolean. So comparing an integer as greater than a Boolean is a very unusual usage. And in fact, here you can see that it occurs in less than 0.003% of similar usages. Now, this is working in this code set, but there are some issues. In C, any non-zero number is considered true, even negative numbers. If a developer were using this library with their own system and potentially had different rules for the value of true and false, this could potentially create a bug. Here you can see the suggestions that control flag came up with. Do you mean to compare your integer as greater than a number? Do you mean that it's greater than a variable? Or do you mean to compare it as equal to true? We reported this anomaly to curl, and they agreed with our findings and decided to update their library. You can already see how control flags pattern-based anomaly detection can catch potential issues that are not caught by rules-based methods. Ideally, this technology could sit within an IDE for real-time error checking, or it could be used for scanning online code repositories. And there are many more possibilities that control flag enables.
Super. So due to time constraints, because it looks like I'm running short, I'll skip over the design, but you're more than welcome to check out the paper online if you're interested. But one thing I would like to point out is for the next steps of control flag, we plan to integrate some semantic reasoning into it. Right now, it's all syntactic. One of the areas that we think the DCEL folks might be able to help us with is understanding this initial semi-trusted data that the humans are making decisions about. This requires us to analyze different environmental variables that help us decide this notion of semi-trust. And then lastly, very quickly, I'll talk just about using genetic algorithms for program synthesis. Some of the strengths for genetic algorithms are listed here. And although perhaps not enough people in the ML community are thinking that genetic algorithms are beneficial, for those of you that might be skeptics, I encourage you to check out Google AI's blog on how AutoML neural architectural search is actually driven by GAs. That being said, there are some weaknesses with genetic algorithms that could potentially make them better. For the work that we are going to be publishing at MLSys, we focus principally on this overcoming the challenge of handcrafting fitness functions. And a fitness function is essentially the function that provides us with the grade of a gene expression as we walk through the evolutionary algorithm. Historically, it's been challenging to handcraft these things, in some cases harder to create the fitness function than just to solve the problem. So what we did is we built the NetSyn system that uses a deep learning approach in the form of essentially a differentiable programming solution to then automatically generate the fitness function. And this will appear in MLSys in just a couple months. Some of the big open questions that we have with NetSyn are really around data. Going back to this question about how are we figuring out what data to use, and in the case of NetSyn, there's a number of different ways to try to train this system. You could use input-output examples. You could use small programs. You could create different DSLs and use certain operations from those DSLs. It's unclear to me exactly how that data should be used. I think this is another area for potential exploration for folks like DCEL, especially what properties might be gained from such data, such as adder distribution support. So in conclusion, we talked very briefly about 4 different areas, but I want to close on just one final slide on the future of machine programming at Intel. As I mentioned earlier, machine programming is a pioneering research. We are hiring PhDs for machine programming research. Please contact me directly if you're interested. We also were highlighted in Intel Labs Day in December. That's Rich Uhlig, the director of Intel Labs there. I encourage you to check that out if you're interested. The second is we have created a new venue called MAPS. It formerly was called MAPL, Machine Learning and Programming Languages, and now it's the Machine Programming Symposium. So if you're interested in this space, submissions are due April 2nd. And then finally, we will be standing up a new Machine Programming Research Center, which is probably something that is perhaps the most interesting to those of you on this call. I can tell you that the call for proposals will come out in Q3 of this year, that I'll be the principal investigator, joint with Tim Matson and Nesame. Greg will be the program director, but I can't tell you anything more than that, unfortunately. So keep your ears to the ground. In Q3, we should have more details. Thanks so much, and sorry I ran slightly over my time.
Thank you, Justin.